Now that's it for distributivity. Now let's look at another property, the final basic property, which is the De Morgan. Laws. So the De Morgan's laws. It's a property in of itself, but it's nicknamed De Morgan because he's a big figure in Boolean logic, and he invented these or he created these just a bunch of logical Boolean facilitations. So the De Morgan's laws property says that if we have, let's say, phi, right? This is I'll just keep saying it until it's fairly obvious. A formula or a variable in conjunction with this psi, and this is equivalent to the negation of psi, of phi in disjunction with the negation of the other variable, which is the psi. So let's deconstruct this in our minds for a second, right? I'm just beautifying this while we do that. So here we have a conjunction, and here we have a different expression, but basically the opposite operator of this. So let's say that what we're trying to say here is the conjunction operator is exactly equal to the negation, the whole negation of the entire operation. So let's say A and B. So there is a notation which is this trace on top. It has nothing to do with the total value of the expression. This is the negation of everything that is underneath, written in another notation which is in Boolean logic. So in the current notation, which is logical formal notation, we use the negation and brackets. But it's simple to see it using this notation, so that's why I'm using it. So what's happening here is that this is basically the same as A negated, and then the negation of conjunction and the negation of B. And that is, let's say that this is around the same of saying A conjunction B, right? And we're saying that the equivalent is the complete negation of the contrary. Except there is some negations in the way, actually. So what happens here is the following. So if we deconstruct this, we get A, and then it has two stripes on top of it. So let's just separate them. And then we have one stripe on top of the disjunction, and then we have two stripes. So we're basically just cutting these stripes. B, right? And what we're saying is, basically by having two, is we're negating A once and then we're negating A twice. So this is a double negation. So we're saying that if A were 0, then we negate it, it becomes 1, and we negate it again, it becomes 0. So this negation negates itself, which means these variables lose their negation, right? However, the operator in the middle is still negated only once. Okay, so that's what this means. This translates directly to this expression. So we're negating this so we're negating this formula once, this variable once, and we're negating this variable once, but we're negating the whole thing once. So it's like putting a bar on top of everything, and putting a bar on top of this and on top of that. And only one bar remains at the end, like we see here at the bottom. And what is this exactly? So the negation, these two are exact opposites. The conjunction and the disjunction offer precisely opposite results. Okay, so any v with the same variables and any v with a conjunction b is the exact opposite of v a disjunction b. Okay, so that established, what happens here is that the a variable, this transforms from negated conjunction into negated disjunction into a conjunction with b. That's what's happening. Okay, so De Morgan's laws, right? Let's backtrack a bit. That off the way. So what we're saying here is it is an equivalent expression, the negation of the whole thing. Correct? So we expand this by saying, to prove that, we expand this in the following manner. So we're saying that this is equivalent to the negation of a negation, because now we know that negations cancel themselves out, of phi conjunction with psi. When you negate these internal variables, you obtain so the negation, the outside negation of psi, so the negation of psi, of phi, yeah. And then this one, because of this negation, gets inverted. So it becomes a disjunction. And then, because of this one, we have to negate, let me bring this to the left a bit. Hopefully you're tagging along the idea. So we have to negate the variable psi. And thus we get the result that is a negated expression with the negation of both variables and the inverted logical operator. That's the proof for the equivalence demonstrated. Righty, now we can say the exact same about the opposite. So let me quickly write this down, or try to at least. Okay, so these are the De Morgan's laws. And this property is the last, let's say, basic consolidated property. There are a few more, and they don't exactly possess a relevant name, but they're already implicit in what's been thought. Like, for example, the negation of the negation. These are, let's say, additional or extra properties. These are extra properties. They are applied naturally. So by saying the negation of a variable is the same as having the variable. Same. So another one is by saying that we have a variable, and let's say we implicate, so it implies another variable. It's the same as saying, so it's the equivalent. Let me just beautify this a little bit. It's the same as saying the negation, okay, of the first variable and disjunction with the following variable. This one is not so obvious, but here's the explanation.